Welcome back to this course in polymer chemistry. In the last lecture, we have started our discussion on polymer molecular determination, and we actually discussed how to get the viscosity average molecular weight. Now, in this lecture, we will start discussing about techniques which will enable us to get the number average molecular weight. We will discuss the technique like membrane osmometry, vapor pressure osmometry and end group analysis, and then following this discussion on how to get number average molecular weight, we will start discussion on determination of weight average molecular weight by light scattering. This discussion may not end this lecture, we will continue in the following lecture. Let us start with membrane osmometry. All of us know about colligative properties, from our physical chemistry knowledges. Colligative properties are those properties of a solution which depends only on the number of solute molecules, provided the solute molecules are non-volatile and we are doing the measurements at very dilute solutions. These properties are called colligative properties, and we know that there are 4 colligative properties: osmotic pressure of the solution, lowering of solvent vapor pressure, elevation of solvent boiling point and depression of solvent freezing point. We will discuss the osmotic pressure method in detail, following by brief discussion on solvent vapor pressure lowering method, and we will just mention about the third and fourth properties. Let us start with membrane osmometry. What happened in membrane osmometry? You have a solution, in this case polymer solution, and the solvent for the solution, separated by a membrane which is permeable only to the solvent, not the solute. So, solvent can go from solvent side to the solution sides, not the solute molecules. Now, this case arises a osmotic pressure difference between the two sides and solvent because of the chemical potential difference. The chemical potential of solvent molecule in this side is higher than the chemical potential of the solvent in this side, which makes solvents to move from solvent sides to solution sides, and thus increasing the pressure. If you have a capillary, then there will be rise in the height of the capillary, and this will continue till this additional pressure compensate or increases the chemical potential value of the solvent this side equals to such a extent that it becomes equals to the chemical potential of the solvent in this side. Similarly, you can design another equipment where you have a polymer solutions in this capillary and which is separated by a semi-permeable membrane which is only permeable to the solvent molecules, and as a osmosis the pressure of the polymer solution side goes up, and this excess pressure here, this excess pressure and this case this are called the osmotic pressure. Now, as we are discussing that this side the solvent chemical potential is higher for a pure solvent than in polymer solution. So, the osmosis happens. Now, So, mu, if we write 1 for the solvent molecule and with this superscript of 0 having for pure solvent at say original pressure P will be equal to the chemical potential of the solvent where the pressure is increased from P to P plus pi, where pi is the osmotic pressure. So, this is the condition for the equilibrium between the solution side and the solvent side and the solution side. So, I can write this and break down this mathematically and just write this one, remember 1 for the solvent and if you generally write 2 for the solute molecules. Solute in this case is the polymer. So, we can rearrange this. Now, mu pi is very small. So, we can just remove the pressure terms from the bracket and we can write from the definition of mu I, we can write using the help of the partial differential. This is nothing but this is the osmotic pressure which we can detect through our measurement and this is the partial molar volume of the solvent and for a very dilute solution which is our working condition, this partial molar volume can be replaced by just molar volume of the solvent. Now, this term we have already determined this term from Florey-Huggins equation in a earlier lecture and this is equivalent to, if you can recollect from your knowledge, this term mu 1 minus mu 1 0 is minus R T phi 2 x, phi 2 is the volume fraction of the solvent molecules, x is the number of segment of the polymer molecules and so on. So, if you compare these two expression, the one we already wrote in this page and the expressions which we know from Florey-Huggins equation, we can write pi is R T So, for dilute solution it can be mathematically shown that we can write the above expression like this, where chi, as you know, chi is the solvent solute interaction parameter, rho 2 is the density of the polymer molecule, Mn is the number average molecular weight. This C is the concentration in mass per unit volume. So, C is concentration mass per unit volume. Now, as you know that this expression, the Fleury-Huggins expression, this is from Fleury-Huggins theory. Fleury-Huggins theory is not applicable for dilute solutions. We can write this expression as a, instead of this we can write this expression like earlier cases, we can write this as a virial expression. So, instead of write this we can write A2C plus A3C square like this, where A2 is nothing but this term. So, this term is nothing but A2. So, this is the expression we can utilize to get the number average molecular weight of a polymer from dilute polymer solution, from its dilute polymer solution. So, what we need to do? We need to make few polymer solutions dilute, so we can make few dilute polymer solutions having different concentration and then measure pi of each of these solutions and then plot pi C versus C, which may be something like this, and then extrapolate this value to C equals to 0. So, this intercept is nothing but pi by C at C is equal to 0. This from this expression, this will be RT by Mn, and the slope will give the value for the second virial coefficient, from which we can get the value for polymer solvent interaction parameter chi. Now, in terms of experiment, what are the things we should remember? One is that temperature control has to be very precise, because osmotic pressure is very much dependent on temperature. So, it has to be very much controlled, and we have to keep all these polymer solutions sufficiently dilute. So, that typically we get or we make solutions having concentration less than 20 gram per liter. Typically, we make concentrations 20 grams, so that these equations are valid. If the solvent becomes good, then the term A3 in this expression, if the solvent becomes sufficiently good, then this term may become significant, which means C square terms may also contribute, and if A3 becomes significant, then C square terms contribute, and if the polymer solvent system is theta solvent for that particular temperature, at temperature of experiment, then A2, A3, this will all become 0, which means it will be the osmotic pressure by C will be concentration independent. This is what happened. For example, if we have, for example, for polymethyl methacrylate PMMA, toluene is very good solvent. So, we start to get contribution from the A3 term or C square term. So, the curve deviates from linearity at high concentration. This is what happened for acetone, and acetonitrile is a theta solvent for the temperature, at this temperature for PMMA, which means the pi by C is be independent of the concentration of solution. So, by this way we can get the number average molecular weight. We can also determine A2 by plotting or getting or determining A2 at different temperature. With this expression from the slope we can get A2, from this slope we can get A2 as you can see from the expression. And if we measure or if we determine A2 at different temperature and then plot A2 versus T, and then the temperature for which A2 is 0, the temperature for which A2 is 0, that would be the theta temperature. So, this is one way we can determine the theta temperature. What are the consideration we must do? As we can see that we do not require any calibration for this method. So, osmotic membrane osmometry is absolute method. So, you do not need any calibration. So, if you make a new polymer, you can get the molecular weight, number average molecular weight from first principle. You do not need any calibration. Now, to make the experiment short, this equilibration between the solvent side and the solute side must be fast. So, equilibration time must be short, which can be done by either by small cell volume or by high membrane surface area. We also need very highly pressure sensitive equipment, because the osmotic value of osmotic pressure is quite low. So, that we can accurately determine the osmotic pressure. And as we can see that for a given concentration of solution, if we increase the molecular weight, the number of molecules goes down. So, if we increase for a given concentration, if we increase molecular weight, the number of molecules goes down, so as osmotic pressure. So, this limits the this method is not capable of measuring the number average molecular weight for very high molecular weight. It can determine typically up to 10 to the power 5 to 10 to the power 6 mole per inverse molecular weight. It cannot determine more than that, because if you increase the molecular weight further, then the osmotic pressure becomes very small. The lower cutoff for this method is determined by the cutoff of the membrane which are used, because if the membrane has a higher cutoff, then the polymers chains which have smaller Mn, that will pass through the membrane to the solvent side, and then it will not contribute in the osmotic pressure. So, we must be very careful that the samples which we are determining the Mn must be devoid of very small molecular weights, otherwise those molecular weights will not contribute in the osmotic pressure, and hence the determined Mn, number-wise molecular weight. So, typically if the soluble, if our polymer sample has quite a few fraction of low molecular weights which are below the cutoff of the membrane, then the Mn or number-wise molecular weight determined by this method is typically becomes little overestimated. So, these are the criteria or these are the parameters we must remember while determining molecular weight by this method. Okay, let us move on and try out or some other points which we must just to add some more points in this membrane osmometry, that the membranes are different for different solvents. For organic solvents, it could be cellulose or gel cellophane. Aqueous, we can use cellulose acetate, nitrocellulose, and if you have a corrosive solution, then we can use glass membranes. Membranes porosity and its distribution must be considered, because that will determine the cutoff, lower cutoff, and its surface area also contribute to the time it require for equilibration. And typically membranes are supplied in a wet conditions in a particular solvent like isopropanol, and so if the solvent you have in your hand is dried out, then this nature might go bad. So, we should not use that. And wet membranes, when they are used for this experiment, they has to first, the solvent has to change gradually to, so that they are wet, when you start the experiment they are wet with the solvent which of our interest. Okay, with this let us move on to the next technique of determining number average molecular weight, vapor pressure osmometry. In this method, these are the two thermistors which are capable of determining temperature difference as low as 10 to the power minus 4 Kelvin. They are placed in a sealed thermostatic chamber which is saturated with the solvent vapor. Now, in these conditions, one with a syringe, in one thermistor one solvent drop is placed, in another thermistor a solution, polymer solution drop is placed. Now, a solution, in the solution the solvent chemical potential is lower than in the solvent. So, the vapor pressure of the solvent in the polymer solution will be lower, and as a result the solvent vapor will condense on this thermistor, and the heat of condensation will increase the temperature of this thermistor, and a equilibrium should arise where the vapor pressure of the solvent in this elevated temperature is same as the vapor pressure of the solvent, pure solvent in the temperature of the thermostat. So, basically we started with a VPO, vapor pressure osmometry. We started say with T initial, which is the thermostated, the temperature for the thermostated chamber which is filled up with solvent vapor, and we add one drop of solution in one thermistor and one drop in the other, one drop of solvent in the other thermistor. So, the vapor pressure will lower and we can write if P is the vapor pressure of the solvent, P1 is the vapor pressure of the solvent in the final temperature, the elevated temperature because of the condensation of the vapor, solvent vapor from vapor phase to the solution phase, which will be equal at the initial vapor pressure. So, that is the equilibrium condition when the condensation stops. This, remember, this is the P1 is represent the vapor pressure of the solvent in solution, polymer solution at this temperature, elevated temperature, whereas P10 is the vapor pressure of the pure solvent at the original temperature. Now, we can apply Clausius Clapeyron equation and write del P del T is del H vaporization by T, Vm is the molar volume, and if you consider the vapor is the ideal gas, considering the ideal gas vapor, we can do few mathematical steps to write this delta T is the temperature difference from the final to initial at T E represents at equilibrium. So, we while deducing we considered that the vapor phase behaves as a ideal gas. Now, because Tf is very close to Ti, we can simply write this expression at P1 by P10 as minus del H vaporization delta T E by R T I square. Now, this term is nothing but ln activity of the solvent. Okay. Now, from thermodynamics we can write then A1 as mu 1 by mu 10 by R T. Remember, this is for T I. So, we are not writing T I. So, these are all T I, initial thermostatic temperature of the medium. So, if you do not mention T I or if you just write T, then that means it is the initial temperature of the thermostated chamber. Now, Fleury-Huygens equation we can write mu I by mu 0 as earlier case we have seen from the osmotic pressure experiment, can simply write this. So, from there we can write that. So, if you start from this, expression we can write R T ln this side, left hand side. So, we can write like this R T. So, if you compare the earlier equation and the osmotic pressure, the derivation we did for osmotic pressure, we can simply write this as this part as minus V1C. V1 is the molar volume of the solvent, 1 by Mn minus delta H preparation, delta Te. So, delta Te by C, K 1 by Mn. So, basically if we can get the delta U, now we can apply the similar experimental procedure like the osmotic pressure measurement. We can make 5 different or few different dilute solutions of different concentration and measure the delta E, delta Te, and then plot delta Te by C with concentration to get Ke by Mn and A2. In practice, we actually do not reach to the equilibrium because some of the heats of the condensation of the droplets actually get dissipated on the thermistor and the solvent stream. So, what we reach is not a true equilibrium, it is a steady state. So, we need to calibrate the experiment with the known molecular polymer solutions to actually determine the number molecular form for the unknown samples. So, this is not a absolute method, we need calibration. So, actually what we plot is delta T delta S by C versus C. Delta T S is the steady state temperature difference at steady state, which again is measured by the difference in the resistance between the two thermistor versus C. So, finally, delta R S by C at C is equal to 0 will give you the K R S, which is this K for the resistance case by Mn. So, we know this. So, we can get the molecular weight Mn for the unknown sample. This is very useful method for low molecular weight samples, because if you go for higher molecular weight, then the increase in the temperature is very low. So, we do not have the techniques to determine so low temperature difference between the thermistors. Typically, we can go up to 10 to the power a difference of temperature between the two thermistors as low as 10 to the power 4 Kelvin, which translate to upper limit of the molecular weight Mn, upper limit of Mn approximately 10 to the power 4 order gram per mole. This is the upper limit of this. So, if you can get more sophisticated instrument which can detect the temperature difference even lower than this, then we can increase the upper limit of the molecular weight determination in this technique. Now, similar techniques, similar methods can be applied to the other two methods, like other two colligative properties. For example, this similarly the same logic can be applied, or same principle can be applied to other two methods like LUV-liometry, which deals with the elevation of boiling point, elevation of boiling point, where delta T E is T b minus T 0, where T b is the boiling point of the solution and T0 is the boiling point of the solvent, pure solvent, and here we require the value for delta H, molar heat of vaporization, and with the help of cryoscopy, which deals with the depression of freezing point, where we can get the same T0 Tf. T0 is the freezing point of the solvent, Tf is the freezing point of the solution, where we need the molar enthalpy of freezing or melting. But these are the techniques are not used much nowadays. These techniques are not used much for several reasons. So, mainly these techniques like osmotic, membrane osmometry and vapor pressure osmometry are used, and as we have discussed that they are complementary to each other, where osmometry, membrane osmometry can determine molecular weight, number of molecular weight for little higher range, and vapor pressure osmometry can be used for determining molecular weights of low molecular weights, low range, lower range. We can also use let us have brief discussion about the third technique, this N group determination. By determining the N group quantitatively, we can also determine the molecular weight. Quantitative determination of N group gives Mn, number average molecular weight. The requirement are that basically we will be able to quantitatively determination of N groups of the polymer. So, polymers must have amenable N groups, which can be analyzed by say titrometry or spectrophotometrically, and concentration must be high enough, so that we can determine the concentration of N group accurately or quantitatively, and the other group presence in the polymer should not interfere in the determination of the N groups of our interest. Secondly, we must know the number of N groups per polymer chain. So, each polymer chain, how many per polymer chain. So, what is the how many chains are there. So, if we have like typically in a linear polymer we have 2 ends, and if you have a branch and it has say 3 ends, then obviously we must know that this case the sample has 2 chain ends N groups, and this case the sample has 3 N groups, otherwise the analysis will be give error in the values. Typically this this method is applied to step growth polymers, because we know the step growth polymers produces N groups, functional N groups and the end. For example, polyester, it has OH and COH groups. So, we can determine titrometrically or spectroscopically these groups. Polyamides, NH2COH group, or polyurethane. So, these are the groups can be determined significantly. This is applicable to again to low molecular weights, because when the polymer chain becomes very high, the number of N groups, the contribution from number of N groups becomes very small. So, detection becomes very difficult. So, this method typically applies to low molecular weights, and typically Mn value of around 10 to the power 4 to in the range of 10 to the power 4 is the upper limit by which we can determine by these methods. We need to what we measure is basically Me is the equivalent mass is M by N, which is defined as M by N. M is the mass of the polymers or concentration of the polymers, and N is the concentration of the N groups. So, Mn would be given by Me multiplied by F, where F is the number of N groups per chain. Okay. So, if we can determine the concentration, we know the concentration of the polymer in the polymer, and what is the concentration of N group which we determined. We can determine N, the concentration of N groups, and then if you know the F, which is the number of N groups per polymer chain, then we can easily get the number average molecular weight. Now, we will give specific examples of determination of N group by spectroscopic method when we discuss the spectroscopic method of polymer characterization in next or 2 lectures from now onwards, when we will give specific examples of how to determine a polymer number average molecular weight by N group determination spectroscopically. Okay, before we move on to other methods of determining polymer molecular weight, namely weight average molecular weight, just to emphasize one point that we know that Mn is very much sensitive to the low molecular weight species presence as the impurities in polymer sample. For example, if we give a specific example, if you have impurities, what are the impurities present in our polymer sample, and we analyze that sample, if the Mn for the pure polymer sample is 10,000, then if we have 0.01 weight fraction of impurity, then the measured Mn of the impure would be about 1500. So, basically even 1% by weight presence of water as impurities is decreasing your determined Mn by several factor, which means we must be very careful about the impurities, especially the low molecular impurities while determination of number average molecular weight, because they have a very detrimental effect in the value we get from the number average molecular weight determination. Okay, let us move on. Let us move to the next topic where we determine the number average weight average molecular weight of the polymers, and we will discuss the techniques of light scattering and subsequently Gim plot to get the weight average molecular weight, and also some other important parameters of polymers like the second variant coefficient and polymer solvent interaction parameter and the radius of gyration. So, what is light scattering? Light scattering, as we know, when electromagnetic radiation interacts with a molecule or a particle, it induces a dipole in the samples, and the magnitude of the dipole will depend on how the charge can be separated. For visible light irradiation, it depends on the polarizability of the medium, of the polarization of the molecules or the particles which is scattering light, or on which the light is bombarded. Now, once this dipole is formed, it oscillates with the electromagnetic radiation, and as we know that oscillating dipole radiates light or electromagnetic radiation. So, in this case this oscillating dipole will emit radiation or electromagnetic radiation at all direction, which are the scattered light. And typically these scattered lights have same frequency as the incident light, but there are cases where there are shift in the frequency of this scattered light than in comparison to the incident light, but these are called inelastic scattering. But for this our scope for this determination of molecular light, we will restrict to only to elastic scattering, where the frequency of the scattered light is same as the frequency of the incident light. So, what is done in the experiments? An incident beam is bombarded on on a sample cell which contains these polymer molecules, polymer solutions, and then the scattered light is detected, the intensity of the scattered light is detected at an angle theta with the incident beam. Now, this intensity of the scattered light can be fluctuating with time, very short time, the time scale is very short, like microseconds to milliseconds. Then you have a fluctuation in the scattering intensity detected by the detector. Now, this from this fluctuation of the scatter intensity, which we can apply techniques, and this is like dynamic light scattering, which take advantage of this fluctuation, and we can get the information about radius of gyration, hydrodynamic radius for the polymer molecules, and the time average intensity, which we will use in the techniques called static light scattering, which will give the information about absolute molecular weight, weight average molecular weight, the radiation gyration, and the second variant coefficient, which in turn give the information about polymer solvent interaction parameters. So, basically the light scattering techniques can be used in two ways: in static light scattering, where we deal with the time average intensity of the scattered light, and second technique can be used where we use the fluctuation of the intensity of the status intensity in dynamic light scattering, which gives the information about the radius of gyration. Let us first talk about the static light scattering, because it gives many information in for polymer solution. Now, as I just mentioned that this light scattering technique can happen for any electromagnetic radiations like visible light or X-ray or neutrons. So, basically the techniques which are utilized to determine or get information about polymer samples are multi-angle light scattering or small angle X-ray scattering or small angle neutron scattering. We will basically restrict our discussion mainly on multi-angle light scattering, and then we will just briefly mention the difference of small angle X-ray scattering and small angle neutron scattering with light scattering, and what are the information you can get from SAXS, SAX and SANS. So, without going much into the theory of light scattering, let us go into the theory directly into the equations for the light scattering from dilute polymer solutions. So, if you consider a polymer solution where, if you consider the polymer solutions, now if you consider its area any area or any particular area from this solution which contain pure solvent and another part content the solute and solute and the solvent. So, each cell on an average, these are the assumption we are taking, and on basis of which we will formulate this scattering equations. Each cell has on average the same number of solvent molecules, but the scattering happens, weak scattering happens because of the fluctuation in the minute fluctuation in the solvent density. And because of the solute molecule itself, the concentration of solute molecules fluctuate either because of the translational motion, Brownian motion of the solute molecules, or if it is a polymer large molecule, there will be conformational changes. So, because of the concentration, effective concentration fluctuation, the light scattering happen from the polymer or the solute molecules. So, what we do to get the information about the polymer molecules or the solute molecules, we deduct the scattering from the solution from the solvent to get the excess scattering. We will explain the terms are in the next page. So, basically in the instrument we try to detect the scatterings only from the solute molecule, in this case a polymer molecule, in a dilute solution, so that there are not much intermolecular interactions, and we deduct the scattering which we detect for or determine from a solute solution from the solvent, so that we can get the information of on scattering from only from the solute molecules. So, we directly go to the scattering equation, which based on the basic Rayleigh equation for Rayleigh scattering, and then also from the fluctuation theory based on Einstein and Smoluchsky. This is for a small molecule, the solute having a small molecule point scatterer. So, we can get a equation like this, where R is delta R theta is, as I said, that the Rayleigh ratio, this is R for Rayleigh ratio, which basically take care of the intensity. It is basically intensity, it is basically the scattering intensity which is normalized with the scattering angle. So, Rayleigh ratio is basically this expression, and delta R theta is nothing but Rayleigh ratio for that particular theta for the solution minus the Rayleigh ratio for the solvent. K is, we define K all the terms which we know. So, for the experiments we know this N0 or eta 0 is the solvent refractive index, dN by dC is the refractive index increment, specific refractive index increment for the solute, lambda is the wavelength of the incident light, N is the Avogadro number. So, we know all these terms, and we define a term called optical constant K as this to make this expression simpler. So, finally, we can get equation like this. So, this expression is valid for point scatterer where no intramolecular interference happen between the, or no interference happen between the scattered light from the same scattered light originate from the different parts of a scatterer. So, basically we can write or you can say that the as a principle, basic principle of light scattering, that first principle, that amount of light scattered is directly proportional to the product of polymer molar mass m, and concentration, and this term which is specific refractive index increment. This expression valid, this is proportional to the concentration only for dilute solution, where the inter solute molecule interaction is absent. Basically, then we can add the scattering intensity from different molecules without considering any interference, destructive interference between them. Now, if we are talking about this expression at point scatterer, where the molecule does not or the scattering from different parts of the molecules do not interfere with each other. If we plot the Rayleigh ratio with different angle, that will gives the same intensity. Remember, we are talking about Rayleigh ratio, which have a cos square theta term in the denominator. If we consider only I theta, which is the I, if we only consider the I theta by I 0, then for small molecules your intensity will look like something like this. Okay. So, this is 0 angle and this is 180 angle, this is 90 degree. But if we plot this Rayleigh ratio, which is, so what we will do, we will start from we are in the next lecture we will discuss the scattering form or angular dependence of the light scattering for large molecule or polymer molecules, which we have angular dependent, the light scattering will be angular dependent. We will start from there in the next lecture.